Hi, everyone. I'm Smrami Patel, and this summer I had also the wonderful opportunity to work in the Khaing Hofstetter lab. And my project focused on, before we can even kind of do neuroprotection, we think about how can we actually characterize that injury. So I was focusing on the significance of grey matter loss on functional recovery acutely after cervical spinal cord injury. So there are about over 300,000 people in the US currently living with a spinal cord injury, and 61% of those actually affect your cervical spine. So it's very important for us to kind of understand the injury before we can even start protecting or treating it. So the main way we can kind of think about and kind of characterize spinal cord injury is that it kind of occurs in two phases, the initial and secondary phase. This is like a temporal way to describe it. So it's not like initial injury doesn't happen and then secondary does. It goes into one. But the initial injury can be characterized by the direct mechanical injury that causes tissue damage. And it starts with the hemorrhaging and the cell death. And then you move about 4 to 5 hours after the injury, you move more into the secondary injury, where there's microglia infiltration, even more inflammatory cell infiltration, and stuff like there is less blood flow. So that is a way for us to kind of see that secondary injury is the more preventable one, and it provides a temporal and spatial window for us to kind of look at. And so another way we can kind of think about spinal cord injuries is looking at the differences between grey and white matter. As you can see in this image on the left-hand side, so the image shows microvessel density in grey and white matter tissue. And as you can see on the grey matter side, there are many more. Actually, it's about 4 to 5 times more microvessels in the grey matter than in the white matter. So if there are more microvessels, it's more vascularized, which means there's more bleeding. Therefore, the hemorrhaging is more serious in your grey matter. So, and that kind of progresses into your white matter, and it's known as progressive hemorrhagic necrosis. And so we already all know this. So what we did, which was very unique with this project, is use ultra-fast contrast enhanced ultrasound imaging to actually see this in long Evan rats in real time while they're still alive. And this enables us to see the perfusion parameters and help us identify risk tissue. So with this motivation in mind, we did laminectomies on long Evan rats between C4 and C6, then conducted baseline scans using this contrast enhanced ultrasound imaging. And then we conducted a spinal cord injury using an IH device, and the injury was placed at the midline segment of C5. So once that occurred, we did more scans after post-injury, acutely after, which was about 30 minutes after the injury, and then again at 4 hours, 24 hours, and 72 hours post-injury. And each one was like a different cohort of rats for each experimental time point. So what we found, we've characterized many hemodynamic changes from that, from all that ultrasound imaging. But something I found particularly interesting was looking at the perfusion deficit. So, and as you can see, perfusion deficit increased as the time point went on. So on the x-axis, you can see the different time points the animals were euthanized. And on the y-axis, you see the deficit volume by fold change, which is just a measurement to show how saturated the blood was in a transverse section. So as you can see, as you increase the time, there is more deficit, which kind of makes sense because there's your injury, your secondary injury is expanding, so there's less blood flow. And you can really see that in the scans on the left-hand side, whereas at baseline, the red really shows the blood flow that's kind of going all the way through the spinal cord, transverse section, whereas at 72 hours, blue is bad, and that's where the injury was placed. And you can see a vast difference between the baseline scan and the 72-hour scan. So this was great, but we wanted to further support this hypothesis by doing immunohistological analysis. And that's where my main part of the project came in for the summer. So once the imaging was done, all the rats were euthanized with an overdose of anesthesia at their different time points for 24 and 72 hours. Their spinal cords were extracted, they were frozen in OTC, and then sectioned, and then we did many stains on them, but the two I'm going to focus my talk on are NEU-N and GFAP. NEU-N, which helps determine neuronal bodies, and then GFAP, which looks at astrocytes. So once those slides were imaged using the fluorescent microscope, we can see that you can see at 4 hours, the size of the contusion injury is much smaller compared to its 72 hours, like vastly different. And also, so GFAP is the astrocyte stain, and you can see them migrating at 72 hours towards the lesion site, which is something that is seen in previous research, whereas like on the left-hand side at 4 hours, you can see that everything else seems relatively fine in the butterfly shape of the gray matter. And also, when I was looking actually at the slides on the microscope, longitudinally, the damage was about 40% more expanded at 72 hours compared to at 4 hours, which really, if we go back, you can see there's about a 40% increase from 4 hours and 72 hours on this graph. So the immunohistological data kind of supports the data we've already seen in the ultrasound imaging, which would be great because that means we can do that in patients without killing them to see what's going on in their spinal cord injuries. So further directions with this is I could see in the microscope like the lesion size was bigger, about 40%, but we would like to do further quantitative analysis on that, looking at neuronal counts and lesion volume to kind of like definitively say those statements. And something else that the lab would like to focus on, and like Lyndon's talk was kind of hinting at, which was like we want to apply neuroprotective drugs to the animals and then do ultrasound imaging and seeing if those perfusion parameters are any different. And then something I would just like to mention is that even though my talk focuses on grey matter loss and a lot of the work in the lab does that, we also acknowledge that white matter is important to functional recovery and neuronal, like how the neuronal networks work in a spinal cord injury. And that is something the lab would like to look at in the future. So I would like to acknowledge everybody in the lab, and especially my PI, Dr. Khaing, and Jeff for helping me so much this summer with like all my questions at any time. I would also like to acknowledge Dr. Ellenberger, Dr. McDonald, and a huge thank you to Sylvia and Julie for like organizing anything and making us all feel at home here. So thank you so much.